Welcome back to part 2 of these notes over periodic trends. So just finished talking about ionic sizes. Moving on here, so reactivity, we talked a little bit about this when we talked about properties of each of those columns. We told you alkali metals are the most reactive and halogens are the most reactive nonmetal, but a little more on your properties here and why. So why? Metals more reactive as you increase, down and to the right. So yes, the second group is also reactive, but the reason why that first column is the most reactive, think about atomic size. So outer electrons held more loosely. The bigger you get, so the more rings that you have around your atom, the bigger you are, the further that outer electron is away from the positive protons. Since it's further away, it's easiest to lose it. It has a very low ionization energy. Since it's really easy to lose, makes it really reactive. So metals want to lose electrons. The easiest one to lose, the lowest ionization energy, is for those biggest elements. For nonmetals, then, it's the exact opposite. These guys want to gain electrons. So where is it going to be easiest to gain? So for nonmetals, reactivity increases as you move towards fluorine. Remember, noble gases, lame and unreactive. They're no fun. You're going to lose the battle of, all right, positive to negative. For fluorine, 9 protons. If it wants to add 1, then it's going to have 10 electrons. So you're already going to lose that battle. But where is that battle going to be kind of the closest? And this is where is the positive charge going to be the closest? So if you look at fluorine with its 7 electrons in its outer ring, 4, 5, 6, 7, and it has this spot for an 8th one. This is fluorine, and then we look at chlorine. You're going to need more room. One, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons in the second ring. 1, 2, 3, 4, 5, 6, 7. And this electron here, positive charge here in the nucleus, where is that square where we're going to put that extra electron? Where is it closest? Where is it going to have the most tug from that positive? Well, that's fluorine. It's close. It's just closer to that positive charge. So that's where that idea of, again, atomic size comes in. Also, something we haven't talked about yet, electronegativity. This is why electronegativity is higher as you move towards fluorine as well, which electronegativity and reactivity are kind of the same thing. So here's that electronegativity thing, the ability of an atom to attract electrons. Again, attract electrons, positive to negative, you just saw that. So here's a chart of the representative elements and their electronegativities. This is something we will use when we talk about bonding later on. Fluorine, highest on our chart, and as you kind of move across a period here, it gets higher as we move towards fluorine, kind of in both directions. So your trend is going to be this way and this way for high electronegativity. So this is ability to attract electrons. Remember, metals, these guys want to lose them, so that another reason why they have such low values. So general trend increases as we go up and increases as we go towards the right. Again, where are you putting that electron? You want to put it as close to the positive charge as possible. Where if I put an extra electron for someone here, it's going in that outer ring. already doesn't, that already has 1 or 2 electrons. All right, so summary of trends. Atomic radius here. Electron affinity we didn't talk about, but actually it's the exact same thing as electronegativity. I should have changed, I've messed up here, I should have changed that to ions. You don't need to know this one, we'll just cross it out. You can draw your own trend for ionic size. First, ionization energy trend looks just like our electronegativity. Atomic radius is here. Remember, we also have trends for reactivity of metals and nonmetals, as well as ionic size. All right, so review here of why all of these things happen. This is something you need to know. All periodic trends influenced by 3 factors. So first is energy levels. Another way of saying that is how many rings, how many shells do you have around that versus that. One is bigger than the other. So higher energy levels are further away from the nucleus. Very visual, very easy to see. The other trend is charge on the nucleus. So think about how many protons you have. More charge equals more pull, because again, they're attracted to each other. You will hear this called Coulombic attraction. It is the fancy word for charge on the nucleus. The third one is shielding. And if you want to think about this as blocking, whatever. But shielding is, okay, positive nucleus here, positive nucleus here. The further out I go, the more electrons there are. 3, 4, 6, 7, 8. So the further out I go, so like right here, there are 2 layers of electrons blocking me from the positive nucleus. Where over here, if I have 1, 2, 3, 4. So 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8 electrons there. Now right here, I now have 3 layers of electrons. So kind of looks like that idea of number of rings, but it has to do with the electrons inside. So not only is the atom bigger, but then there's also more electrons in between, which just means less and less of this positive charge makes it out here. So this actually causes it to be, depending on what the trend is, bigger or less attraction than even size. So these kind of work together with the atomic radius, but they are 2 separate things. All right, so what do they influence? Energy levels and shielding. So like I said, they work together. They are 2 different things, have an effect on group trends. So all group trends we can explain in terms of number of energy levels and shielding. Please go more into depth than just saying energy levels and shielding if I ask you to explain. So tell me why. Tell me there are more energy levels in this versus the other one, or there are fewer, or something like that. Shielding, tell me there are more electrons in between the nucleus and where we are putting this electron, or something like that. Don't just say these 2 words and think that's good enough for an explanation. And then Coulombic attraction is the only effect on a period. There is only one. So again, think about as you work across your periodic table, if we look at that 3rd row, you have 3, well, the 2nd row, you have 3 protons, you have 4 protons, 5 protons, 6 protons, and so on. You are adding more positive charge as you go across a period, and you're putting those electrons in the same orbital, the same ring. So it takes away this. It takes away this because there's still the same amount of electrons in between the nucleus and those outer electrons. So it's just the fact that we have more protons to hold them in. And that is all. Hopefully you got both of those videos. And again, focus on applying those, especially what we just saw right there, those the reasons why, to periods, groups. If I give you a set of elements or a set of atoms, you should be able to tell me which ones, how those trends affect that set, even more than just a group and a period.